One of the most powerful methods in investigating the convergence of a infinite series is using the ratio test and a bit of a lesser extent the root test. So the ratio test is the more common one that we'll discuss today. So let's start with the ratio test. Here's a theorem that validates the use of the ratio test. So let AK, the sum AK, be an infinite series, and let R, and this is important, be equal to the limit as k goes to infinity of the absolute value of AK plus 1, so the k plus first term, and over AK. You're going to take the absolute value of that ratio, so one term and then the next term, and take the limit of that ratio as k goes to infinity. And we have the following cases. If R is strictly less than 1, the series converges absolutely, and therefore it converges. Okay, absolute convergence implies convergence. Okay, it's stronger. So if R is strictly less than 1, we know the series will converge. In fact, converge absolutely. If R is strictly greater than 1, including the situation where R diverges, the series diverges. And if R is equal to 1, the test is inconclusive. So you can't conclude whether the series will diverge or converge. So let's take a look at a concrete example with using the ratio test. Use the ratio test to determine whether the following series converge. So let's start with A. We have this series right here. And we start with the form, limit as k goes to infinity of AK plus 1 over AK, and the absolute value of that. And so what do? You just take, for the AK plus 1 term, wherever you see a k in the series, you just put a k plus 1, as we've done here. And here's the AK term. And when you divide by a fraction, you multiply by the reciprocal. And you'll get that ratio right there. And we don't need the absolute value anymore because this is always positive anyway. And this k plus 1 factorial is k plus 1 times k minus 1, dot, 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 all the way till you get to 1. And so we break that k plus 1 factorial term into a k plus 1 times k factorial. And now you could see that the k factorials will cancel. The 10 raised to the power of k will cancel as well. We break up that 10k plus 1 to 10k times 10, taking advantage of the property of adding exponents when you multiply such numbers together. And we'll ultimately get 10 over k plus 1, take k to infinity, and that's 0. And that's strictly less than 1. And so the series converges. In fact, it converges absolutely. And let's pause for a second and see why the ratio test was so helpful here. Okay, now we could have done the sort of integral test, but integrating a factorial, that's very tricky. Okay, and so in general, if you have exponents in factorials, and this isn't laid in stone here, but just as a general methodology, then you're very likely going to be using the ratio test. Okay, so that's usually a hint when you see factorials that you're likely going to be using the ratio test, because we could get these cancellations. All right, let's take a look at B. Again, another sort of factorial term in there. And this time we actually have a alternating series. Okay. And so, we could, because it's an alternating series, try to prove this with the alternating series test. But we want to use the ratio test. And so we'll do that. All right, so we write out the terms again, and wherever we see a k, we put a k plus 1 for the term in the numerator, and we'll end up with that ratio there. And we start getting cancellations again, sort of typical of these problems. And notice we break up that k plus 1 raised to the k plus 1 in terms of k plus 1 raised to the k times k plus 1 to get that additional cancellation. And then we have this ratio here. And as you'll recall, I mean, this is one of these common sort of problems. And you do get the indeterminate form 1 to infinity, 1 raised to the power of infinity. But you could take the logarithm and then take the limit of that and then exponentiate at the end. And you will get that it's equal to e. Okay, it's one of these common ones that students tackle in Calc 1. E is about 2.7, so it's strictly greater than 1. And so we know the series diverges. And alternatively, the divergence test would have given us that result too. We'll recall from the growth rates that k raised to the k grows faster than k factorial. It's one of these sort of rare functions that grow faster than the factorial. All right. Finally, we'll tackle C, and we look at that again. There's an alternating series there, so we may opt to do the alternating series test. But we also have an exponent, and that's grounds for trying the ratio test. Let's do it using the ratio test. So again, wherever we see a k, we put a k plus 1. And one of the terms already had a k plus 1, so that's where that's getting k plus 2. But either way, the minus signs are going to get taken out by the absolute value. Okay, so we take the absolute value of the ratio, and so minus signs don't really matter. And so we do our simplification and then take the limit as k goes to infinity, and we get 1 over e, and that is strictly less than 1. And so this series converges absolutely, and hence also converges by the ratio test. I make a remark here that the ratio test is inconclusive for 1 over k. You could, as a practice problem, take the ratio of k plus 1, 1 over k plus 1 divided by 1 over k, and you should get that the limit is 1, and hence here's just an example of a series that the ratio test is inconclusive for, but we know that this harmonic series diverges by the p-series test that we looked at. So now let's look at the root test, okay? And the root test is often used when you have like a single term raised to the power of k. It becomes convenient there. Oftentimes, any sort of series that you could tackle with the root test, you could tackle with the ratio test. So it's more common to see the ratio test being used than the root test. Nevertheless, we'll cover it. So let ak be an infinite series, and let rho, this Greek letter rho, be the limit as k goes to infinity of the kth root of the absolute value of an arbitrary ak term. And just to emphasize this, the kth root may also be written as this, raised to the power 1k, 1 over k. All right, so let's take that limit as k goes to infinity. We get this rho, and now we have some cases. If rho is strictly less than 1, the series converges absolutely. And of course, if it converges absolutely, it converges. And if rho is strictly greater than 1, including if rho diverges, then the series also diverges. If rho is equal to 1, the test is inconclusive. So let's take a look at a concrete example. Use the root test to determine the whether the following series converge. So we take a look at this. I mean, this is a prime example of where the root test is useful. You get this whole term raised to the power of k. Okay, and right off the bat, that's obviously one that is most likely more easily solved using the root test. So we'll take the limit as k goes to infinity of the kth root of the absolute value of an arbitrary a sub k term. Okay, so we just plug that in. We have this 1 over k, and then we have this term raised to the power of k. And, we do have this property that x to the k 1 over k is equal to x to the k times 1 over k, okay, which is equal to x to the 1. Okay, you can multiply exponents together. And so these k's cancel, and you end up with that term there. Taking the limit as k goes to infinity, you could multiply the numerator and denominator by 1 over k squared, and you'll get 4/7. That's strictly less than 1, and therefore the series converges absolutely, and therefore converges. Now let's take a look at B. And right off the bat, you have an exponential term over a polynomial, and exponential terms will dominate. Okay, so the divergence test will give us that this series will not go to 0 and therefore diverges, and these terms will not go to zero, and therefore by the divergence test it diverges. Nevertheless, let's tackle this using the root test just to see how it works. So we take the kth root again of this term, and the absolute value here gets rid of the minus sign. Okay, and even up here, here we had 3 minus 4k squared, and this term is negative for values of k greater than or equal to 1. And so that's why we have them flipped around there, so that we multiplied this term by -1 to make it positive. And that's what you do with the absolute value. So absolute value of x is equal to x when x is positive, and negative x when x is negative, so that you always end up with a positive number. All right, so we'll take this 1 over k. Again, the k's cancel, and we get this 10 over k. And now we're going to take out that 10 and write this term this way. Okay, we do that because this k over 1 over k is one of these common sort of limits that we tackle, and it's equal to 1. And so you get that rho is equal to 2, and that's strictly greater than 1. The series diverges. Okay, the ratio test would have also worked on these two examples. Nevertheless, the root test is quicker, and the root test is inconclusive for the harmonic series. And to see why it would be inconclusive, I mean, although it's one of these typical examples, we'll go ahead and do it. So if you, this k raised to the power 1 over k, that's the infinity to the raised to the power 0 indeterminate form. And so we'll take the natural log of that term, and we're taking the limit as k goes to infinity. We'll exponentiate whatever we find of the limit of the natural log at the end. So we'll have 1 over k natural log by the property of logarithms. Now we have the indeterminate form infinity over infinity, and there we just apply L'Hopital's rule, and we get that the derivative of natural log of k all over the derivative of k, and we end up with this term here, and that's 0. Okay, and so our limit of the original series, okay, limit as k goes to infinity of k 1 over k is equal to e to the 0 or 1. Okay, we use that property up here, and you would get a similar term for doing the harmonic series, and so you get 1, and That just shows that the root test is inconclusive as well. Okay. And so we also got an example of where the root test, for the harmonic series, this series here, we had to use the integral test. Okay. But these are examples of the ratio and root tests, and it's yet another tool for testing the convergence of a given series.